What I'd like to do in this video is go over this example that says during a reversible process executed by a non-flow system, the pressure increases from 344.74 kilopascals to 1,378.96 kilopascals in accordance with the relationship PV is equal to C. The internal energy increases by 22,577 joules and the initial volume is 85 liters. And we're asked to figure out the heat transfer into or out of the system. Now, in order to do this, a good place to start would be our energy balance equation. Our energy balance equation says that our change in kinetic energy plus our change in potential energy plus our change in internal energy is equal to Q, which is what we're looking for, the heat into or out of the system, minus the work done by our system. In our case, in this example, the change in kinetic energy and potential energy is 0. So we can rewrite this equation as Q, what we're looking for, the heat into or out of the system, is equal to our change in internal energy plus the work done by the system. We know that our work done by the system is going to be the integral from V2 to V1 of P with respect to our volume, so with respect to dV. Now, we need to figure out what V2 is, what V1 is, and a relationship or a formula for P. So let's start with what's given. We know that V1 is equal to 85 liters, but that's not really a unit we want to work with. We want to work with stuff in meters cubed. So we're going to multiply this by 0.01 meters cubed because that's in what's in 1 liter. And we're going to get our volume is equal to 0.085 meters cubed. We know our P1, our initial pressure, is equal to 344.74 kilopascals. Now, we're not sure what V2 is, but we do know that P2 is equal to 1,378.96 kilopascals. And we're also told that it's increased with this relationship P to the PV is equal to C. So what does that mean? That means if I say P1 times V1 is equal to C, then I can get a constant for C, and I can figure out what V2 is. So I have 344.74. This is kilopascals times 0.085. This is meters cubed, and this is going to be equal to 29.3029. And what is this unit right here? Well, let's dissect what a kilopascal is. A kilopascal is going to be 10 to the third pascals. And a pascal is a newton over a meter squared. Now, meter cubed is just a meter cubed. So when we multiply these two numbers together, we're going to have 10 to the third newton meters. And what is a newton meter? A newton meter is just a joule. So we have 10 to the third joules, or we have one kilojoule. So this right here is in the units of kilojoules. Okay, so now we're going to use this relationship again. We're going to say that P2, V2 is equal to C. We know what C is. C is equal to 29.3029. We're going to divide pressure. So we're going to divide by 1,378.96 kilopascals. And this is kilojoules. And we're going to get our volume. V2 is equal to 0.02125 meters cubed. So here's V2, here's V1, and that's what we need for our integral. So if I write my integral again, right here, I have my work is equal to the integral from V2, which is 0.02125 meters cubed, to 0.085 of, we need an expression for what P is. Well, we're going to use this equation one more time, and if V is equal to C, then P is going to be equal to C over V. And this is what we're going to put inside the integral. So we're going to say that this is equal to C over V dV, and C right now is a constant, so C can be taken outside of this integral. So our integral that we're going to solve is going to be equal to work is equal to C times the integral of V2 to V1, 0.085 of 1 divided by V, I don't like it there, 1 divided by V dV. And what is this integral? This integral is nothing but the natural log of V. So we're going to have our work is equal to C times the natural log of V, where the natural log of V is evaluated from 0.0215 to 0.085. And I think I have one more line I can squeeze onto the screen. So this is equal to C times the natural log of 0.02125 minus the natural log of 0.085. And what happens is we're going to use a natural log identity to say that this is equal to our work is equal to C, which is 29.3029 kilojoules. Let's leave the units out right now. Times the natural log of 0.02125 divided by 0.0851. And this can be evaluated numerically, and when we do that, we get that our work is equal to minus 40.6224 and kilojoules. Right here, this has a unit of kilojoules, this has a meters cubed. These cancel out and we're left with kilojoules. So our work right now is minus 40.6224 kilojoules. We're going to place it into this equation. Here's my delta U. This 22,577 joules. So Q is equal to 22.577 kilojoules plus this minus 40.6224 kilojoules, and I get my Q is equal to minus 18.045 kilojoules. So that means that this amount of energy is leaving our system, minus 18.045 kilojoules.